Okay, about the course. The focus of the course would be socio-technical, from the socio-technical viewpoint. Uh, and I would like to have very kind of interactive session with you. So just one question to you all. Whoever has the answer, please feel free to talk. What do you, when I talk about socio-technical, what does it really mean? Can anyone tell me? What does it really mean? Anyone? Can anyone tell any comment? What is socio-technical? Okay, no comment. Okay, maybe then I can explain. Yeah. So so as you know that there are technologies, for instance, blockchain, AI, and so on, and there are many other technologies. But what happens? These technologies are actually used by humans. They are used by organizations. They are used by the society, right? And ultimately, we develop software, we develop blockchains, we develop, whatever technology. We develop it for the society, for the organizations, for the humans. So this means that the technology and the society at some point interact. So as you can see in this figure, in the middle part is the socio-technical system. So basically, the technology is developed for the society, and then the society uses the technology, and then there are some phenomena that is created when this technology and society interact. So that kind of those phenomena is called socio-technical. So if you look at the content or the name of the course, this smart contract for business applications or blockchain for business applications. So why will you do that? I mean, we are developing the technology for the businesses. This means that we are developing for the society. So ultimately, we need to have the socio-technical viewpoint because our technology is for the society or for the business. So that's why I say that the focus will be on the socio-technical perspective. So I will try to cover both technical and business aspects. The technical, the concepts I will cover, then I will show you the implementation, and then I will also show you the business logic. And then again, as I was telling, that my goal is to provide some knowledge to you, everyone, irrespective of your background. So I asked about, what is your background, and you mentioned that most of you coming from computer science, maybe with few exceptions, and then some are students, some are job holders. Some have very limited knowledge on blockchain, and some have a little bit more. So the content has been made in such a way so that everyone has some kind of takeaways. And the content of this course has been adapted from different research articles published in software engineering and information systems and other domains. And then as I was mentioning at the very beginning, that I have been conducting research on blockchain since quite long time, and then I'm running many projects. So I will try to bring something from my own research work And then some things will be covered from white papers, for instance, Bitcoin, Hyperledger, case studies, and so on. And then some of the content has been adapted from various online courses on blockchain as well. So it's a kind of a mix of many things. This course will help you to understand the basics of blockchain and its use cases. For instance, today we will talk about these basics of blockchain and its use cases. And then you will be able to solve problems using a blockchain. For instance, tomorrow I will show you some example smart contracts, how to write smart contracts, and so on. And then overall, the course will provide you a broad picture of the research advances on blockchain and what in the future you can expect. And of course, as I was mentioning in the previous point, that it will provide you some future research opportunities. For instance, if you want to write your bachelor thesis, master's thesis, or you want to do a PhD, so maybe you could be able to find some guidelines or some research topics that you could take a look from this lecture from this course. And then the most important part is this, that you will be able to participate in any types of intellectual discussions with your peers related to the topic area, related to blockchain, related to smart contracts, related to its applications, including cryptocurrencies and so on. Yeah, about this classroom interactions. Yeah, I would like to have a very interactive session. A very interactive session. This means that it's not that I will always speak. So I will ask you to hear about your perspectives on topics. I will put a question and I will ask you your opinion. Please feel free to talk and try to remember there is no right and wrong answer. I understand that some of you are very new in this topic, but don't worry. Just ask questions. Just let's talk. If we talk, if we interact, then maybe then we will learn more. So feel free to talk when I ask a question, and don't hesitate. And then there will be some discussions, not really group discussions, but here we will discuss about things. And then maybe let's see if we can really do it. If there is some group work, then you can present the things. But maybe I'm not really sure if that can be done, but we will see. But the point here is that let's talk. I mean, we just don't hesitate. When we interact, we learn more. Any questions so far? Okay, if no question, then I move to today's agenda. And today I will try to give you some very basic vocabularies on blockchain. As some of you have mentioned that you have limited knowledge on blockchain, so I think providing some basic vocabularies is very important. And then we will also talk about a little bit about distributed ledger technologies, distributed computing. And then we will talk about blockchain architecture, blocks architecture. And then we will briefly talk about mining process. And then we will see how much time we have. and then maybe I will show you a few use cases. But let's see. Okay, distributed ledger technology. Have you heard about it? Anyone? What is it? Anyone? Maybe those who have intermediate knowledge on blockchain, maybe you can say something. What is it? Anyone? Okay. It seems, yeah,
So
yeah,
that data is stored on different computers than storing on central server.
yes. So a ledger that is stored in different computers. That is what you said, right?
Yes.
Yes. Very good. Very good. Anyone, anyone else wants to add something on top of it? Okay. If not,
Good
then I
morning.
will go to the next
As per,
question. Yeah, yeah, yeah. Please, please. Yes.
it is as per my knowledge, it is a decentralized ledger system which is stored in different peers, and
Mm-hmm.
we transaction based upon the information placed in different peers only. There is
Yes.
no central body it.
Yes. 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 Very good. Very good. You have explained it. But then the next question, what is its benefit? Why would we like to store it in different computers, different nodes, rather than a central entity? What is its benefit? Can you tell me what is the benefit of putting the things in different places rather than one place?
Sir, it will create a transparency between the ledger system.
Transparency, yeah.
And
Yeah.
if it is not centralized, then if any mishap happens to any node, it will not affect the whole transaction.
Yes. 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 Good. Yeah, and then anything other people can want to add?
Yes, sir.
Yeah.
Uh, this is a decentralized, so no central authority.
Mm-hmm.
And second is effectively reduce intermediates, making process faster and cost effective.
Yeah. Yeah. Okay. Yeah. Yeah. But another point is there. Let's say the single point of failure, you have heard about it. Or let's say that if if the center, one place get one place, like if you have the central entity, and that place, that data is somehow corrupted, still you have other copies in the network, other good copies in the network, right? So that is another benefit, that it is not in one place, it is distributed in many places. So if in one place something happens, still have the copy in other places. Okay. And then the next question is, how can we have a DLT, or how can we build a DLT? And the answer is that blockchain is one way to build distributed ledger. So blockchain is one way we can have distributed ledger. However, there are other ways. For instance, hash graph is another way. But in this course, we will talk about mainly blockchain. So the idea here is that we are talking about distributed ledger technology using blockchain. Now let's take a look in the computing history and why we are so much interested in distributed ledger. Uh, I can say that there is a trend toward decentralization from centralization in computing technologies and architecture. So what I'm saying here that we are moving, if you think about the computing history, we are moving from centralization to decentralization. And why I'm saying this, so there is an image here. Can anyone guess what is this image? What is this picture? Any guess? Just make a guess, no problem.
Is that a mainframe?
Yeah, very good. Mainframe, yes. Yeah, so mainframe computer. This is a mainframe computer. And think about the mainframe computer. It's very much centralized. And this mainframe computer possesses all the processing power and storage. There is nothing outside of it. So everything, in this machine, it is not connected to any network or anywhere. It's just the machine. In this machine, all the processing power is there and storage is there. So very much centralized in one place. Okay. So, many years ago, we had only mainframe computers like this, very centralized. And then as we move forward, then we have this. We got this in 90s or late 80s or early 90s. We got this. What is it? It is easy, of course.
Personal computer.
Yeah, personal computer. Yeah. So then the personal computers came. And when the personal computer came, at the same time, this client server architecture came. So this means that there will be a server and there will be a client, and then client can connect to the server and then synchronize itself with the server. So as you can see that here, this client server architecture is a little bit less centralized than mainframe, because now your personal computer also has some processing power, storage capability, and server also has processing power and storage capability, and they can sync with each other. So basically the same copy could be there in two computers, in the server and in the client. So we can call it less centralized than mainframe computer. Okay. And then as we move forward, this thing came. Any guess? What is it? It's difficult to guess, but maybe still you might be able to do it.
Cloud
So
computing.
cloud computing.
Oh yeah, so it's very easy then. So several people said it. Okay, very good. Yeah. So internet and cloud computing. Then internet and cloud computing came. And as you can see, that variety of devices can connect. Your smartphone, IoT devices at your home, computers, everything. So we can say that, this is decentralized in compared to uh, this client server architecture. So this is more decentralized or distributed. So, and then the same copy you can have, let's say, on your phone, on your computer, laptop, office laptop, home laptop, and so on, with your friends, and so on. But the main problem here is that the cloud. Who is providing the cloud? The cloud is provided by a corporation, a single entity. So yeah, definitely they have made it distributed. Maybe they placed servers in different countries. So this is distributed, but who think about the ownership? The ownership is still of a single entity. For instance, if you think about cloud, so the owner of the cloud, maybe IBM, Amazon, Facebook, Google, they are the owner. So on one single entity is maintaining the cloud. So this means that you need to trust this one single entity, the middleman. You need to trust that entity, that your data will be secure, will not be lost, will not be shared with some other parties without your consent. So you need to trust this middleman. So that is the problem. So in this architecture, things are okay, but you need to trust a single entity. And then this thing came. And this is the distributed ledger technology. And what is basically doing, it is removing the middleman and doing the things peer to peer, and everyone keeping a copy of it. So distributed ledger technology is about providing control to the end users without need for the middleman. And here, as you can see, the trust is distributed. And somebody also said that here, when you have DLT, you have more transparency because everyone has one copy. If one copy is lost, still the network has copy. The network has multiple copies somewhere else. Okay, so let's now try to summarize. What is DLT? So DLT is a type of data structure that resides in multiple computing devices across the globe. So you have already said it. And blockchain is one way to build distributed ledger technology. As I was mentioning before, that there are other ways, but blockchain is one way to build it. Yeah, I just mentioned that there is other way, for instance, Hashgraph. And then one very important distinction is that blockchain is not Bitcoin, because I think the problem has been whenever you talk about blockchain, it has got a negative sentiment. And the negative sentiment is because of Bitcoin and cryptocurrencies. The market is kind of a scam a little bit, not if not fully, but the cryptocurrency market, is very volatile. So people think that blockchain means cryptocurrency or blockchain means Bitcoin. But that is not the case. So blockchain is not Bitcoin. Rather, Bitcoin uses blockchain to record transactions. So Bitcoin is one application, but one very important application. Bitcoin is an application of blockchain. And DLT existed prior to Bitcoin. I think the history of DLT is much old. If you read I think the Wikipedia, you will find the source. But it's much older than Bitcoin. Bitcoin is only 2008, 2009. So DLT was there some 20 years, more than 20 years ago. I mean, from here, I think 45 years from now, it was there. Or if not 40, at least 30 years. Uh, then, but Bitcoin is the first application on blockchain that uses cryptography, the CIA techniques. I will cover those CIA techniques later. And then peer-to-peer network and a consensus algorithm to verify the transactions. So Bitcoin, or in general blockchain, uses cryptography. I will show how it actually works in practice. I will show you later. And then peer-to-peer network, and then a consensus algorithm that is used to verify the transactions. So now, what is blockchain? The question is, what is blockchain? Anyone? So now you know what is DLT. Now, can anyone tell me what is blockchain? Anyone? Yeah.
So blockchain is a collection of blocks which stores transactions
Mm-hmm.
which are ever growing.
Yeah. Okay, very good. And ever growing, very good. Anyone else
So
want to add
blockchain
anything?
is a type of distributed ledger technology that
Yeah.
records transaction in a decentralized, immutable, and insecure manner.
Yeah, secure manner. Secure manner. Yeah. Okay. Okay. Good, good. Anything, anyone else? Anyone else wants to add? Yeah. Yeah, please go ahead. Okay, maybe it was just noise. Okay. Okay, thank you. I think you have covered the most important parts, but let's see what I have here. So yeah, someone already told that blockchain is a distributed ledger to record transactions. So yeah, I have it here. And then someone also mentioned that blockchain creates a chronological chain of blocks. Therefore, its name is blockchain. So you already mentioned. And each block contains a list of transactions bundled together. But what is very important is to understand blockchain is not just about transactions data. It's not about this financial transactions data. But in fact, any data you can put it in the blocks. So any type of data, for instance, medical records, property agreements, any data you can put it in the block. So it's not just about transactions, but any data you can put, depending on the use case. And then the first block is called Genesis block. The very first block in a blockchain is called Genesis block. And each block is time stamped. And each new block refers to the previous block. So this is how a chain is created. So each block has a time stamped written. And then when a new block is added, it is added at the end and it has a pointer to the previous block. With cryptographic hashes and timestamp, a blockchain creates immutable data. So again, somebody has already mentioned that blockchain is about creating immutable data. Okay. So in other way, if you try to define blockchain, so blockchain is a peer-to-peer distributed ledger forced by consensus combined with a system for smart contracts and other assistive technologies. And together, these can be used to build a new generation of applications that establishes trust, accountability, and transparency at their core, while streamlining business processes and legal constraints. So I think everything you know from this slide, but about these smart contracts and consensus, we will define them in a much better way later, and we'll see the examples also.
Sir, I have a question.
Yeah, sure, go ahead.
Sir, not all blockchains can run smart contracts, right?
Yes, not all blockchains can
So
run
that
the
in the
smart contract.
definition you have mentioned, can you go back to the definition?
Yep, yeah, yeah,
So, so
yeah.
this definition is not general for all
No,
blockchains.
no,
Yeah. Okay.
no. You're absolutely right. And I think those things are there in my other slides. So maybe just I can briefly mention. So Bitcoin, for instance, does not really have that much smart contract facilities. But then Ethereum, from Ethereum, they have smart contracts. So yeah, so the blockchain 1.0, the very first blockchains, group of blockchains, they didn't have smart contracts. Okay, then in blockchain, uh, there is the concept of this, this mining process. Mining process is also this consensus algorithm. So who maintains the blockchain? Let's say that if something, so a new data comes, a new transaction comes, I mean, then how it is validated? Because there is no central entity. And there, this consensus algorithm comes into play. And one of the consensus algorithm is called proof of work. I will cover more detail about proof of work later. But for now, just try to understand, try to think this way that okay, there are some nodes or some people or some nodes, some which we call miners. So what they do, these miner nodes bundle the valid transactions into a block, and then miners need to solve a cryptographic puzzle to find the new block and inform to the other miners in the network. So miners are responsible to validate the transactions or validate the data and add the data in a block and then add it to the blockchain. So instead of a single entity, this miner, miner does this thing. And the process is known as proof of work and requires significant computing power. And this is the consensus algorithm that is used in Bitcoin. And if you think about each block, a block, what does a block contains? So each block contains, as I was mentioning in the previous slide, that it refers to the previous block. So this means that it includes the reference to the previous block. And then the next one is called proof of work signature. So the miner who finds the block, signs it, and also it's called nonce. I will give you a very practical example later, then you will understand. And then timestamp is mentioned, written, and then the transactions included in that block. So these are the things that each block will have. Just try to remember a little here, but I will show you some images and it will be much more clearer at that time. Yeah, so this image. So in this image, you can see that there are 4 blocks, block 51, 52, 53, and 54. So 51 is the oldest block. Block 51 is the oldest block. And block 54 is the newest block. And take a look in one of the blocks. So let's take a look at the block number 54. And in this block, you can see there are some transactions. Transaction, 3 transactions, you can see. Okay, so 3 transactions are there in this block. And then if you look at previous block, so as I was telling in the previous slide, that each block will refer to the previous block. So now you can see that the previous block of block 54, which has many zeros at the beginning and then 90B4. So this number, this number is same as the proof of work of block 54. And if you see the arrow there, so it is referring to block 53. So block 54 is referring to block 53, and block 53's previous block, if you look at the characters, the numbers there, number and characters there, you can see that it is referring to block 52, and then block 52's previous block is referring to block 51. So this is how it is changed. So as you can see that it contains some transactions and then the proof of work signature and then previous block. And the previous block is the proof of work signature of previous block. So this is how it is chained. Now here one point I have added is that, so I have said that block 54 is less secure, but from block 54, when you move toward block 51, security is improved, more secure. So what I'm saying here that blocks are more secure as you go further back in the chain. Why is that? Can anybody tell me why is that? Why block 54 is less secure to attack than block 51? Or why block 54 can be edited or can be updated easily than block 51? Can anybody tell? Any guess?
So
Somebody
because
has
the
started.
so
Yeah.
because the hash of block 54 is not stored in any other block.
Yeah, kind of. Yeah, kind of.
See, if you see block 52 and 53, these blocks are connected to the block before and after it.
Yes,
That's
yes,
50.
yes, yes. So, yes, anyone else? Yeah, yeah. I think you have answered it partly. And as they are connected, let's say if you want to change something, if an attacker wants to change something in block 51, then he has to recompute everything. He has to recompute block 51, block 52, block 53, block 54. Because changing B51 basically means changing 52, 53, 54 because they are chained. So all the values will change, all the things will change. So So he has to change everything, all 4 blocks, to make sure that he can change block 51. However, if someone wants to change only block 54, then he can change only block 54, and there is no impact on block 51, block 52, and block 53. So if somebody wants to change block 51, for instance, he has to gain a lot of processing power and recompute everything, all blocks. Whereas for changing block 54, he doesn't need to recompute all things, just he can recompute block 54. And this is why, changing any old transactions, any old data in blockchain, old blocks in Bitcoin network is very difficult, is impossible, almost impossible. However, the newer one, of course, very difficult, almost impossible, but is still relatively easier. And that's why I have written here that blocks are more secure as you go further back in the chain. You got it? Yeah, okay. Yeah. But then this is so the concept of Merkle tree is very important because at the end, the transactions that I'm showing here in this figure, that it has 3 transactions, they are not really stored in this way. They are actually stored, but instead of that, they are stored using this Merkle tree. And that's why it is very important to understand the concept of Merkle tree. So here, in this figure, we have three blocks: block 1, block 2, and block 3. And as said, that in each block, let's say in block 3 header, you can see that it is pointing to the previous block with this first thing, previous header hash. So it is pointing to the previous block. And then it has this Merkle root. But very interesting thing is that with this Merkle root, it captures all the transactions with one root. It captures all the transactions. So, and how it is really done? So let's take a look on this block 2 headers Merkle root. And let's take a look on these transactions, block 2 transactions, where you have transaction A, transaction B, transaction C, and transaction D. So what you really do is that, let's say the transaction 1, you calculate the hash of transaction A. Sorry, not transaction 1, but transaction A. So hash of transaction A, and then hash of transaction B, you calculate. And then you calculate again hash of transaction A and hash of transaction B. And similarly, for transaction C and transaction D, you do the same thing. And then you all together, it creates the Merkle root. So in the Merkle root, ultimately, you will have only one sequence of numbers and characters. But with that one sequence of number or characters, you will represent all the hashes of that block. So all 4 transactions are then included in one number. All transactions, all 4 transactions are then in the one root, on Merkle root. So this is how this Merkle root is calculated, and you store Merkle root in the block. Okay. So now let's take a look at this this block header data fields. What are the things they have? considering Bitcoin as an example. So, in these examples, I have shown you that it has, a previous header hash, it has Merkle root, and so on. But, actually, how does it look like? So this is how it looks like. So it has a version in the header file. It has a version, and then as said, yeah, Amitesh, you have a question. Go ahead.
Good day, sir.
Yep.
My name is Amitesh. I wish to ask you that since Merkle root is being in the block header, so
Yep.
I wish to know, since it is storing the hash of all the transaction
Yep.
in the form of root hash. So
Yep.
whether all these transactions are also stored within the transaction data part.
No. I think in order to reduce the block header size, you just keep the root, and if there is some problem in the root, if there is any change in one transaction, then the root is completely invalid immediately. So it is then helping to verify faster that the block is 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 right. So as you can see here, the header file contains Merkle root, the number 3, and then the previous hash, and then time, beats, and nonce. So the header file only contains Merkle root, not other things. The header files only include Merkle root. Yeah. Okay. So as I was telling, that version is there, and then previous hash. So as I was showing in the previous picture, yeah. So what is Pravisha? Pravisha, you have a question? Please go
Yes,
ahead.
yes, sir. Sir, this block header values are also verified during consistency process. These hash values. How do we?
Hash.
Uh,
Yeah, I will show you. When I will show you the examples, then maybe things will be clear. I think next. I think in 1 or 2 slides later, you will have those examples. Then probably it will be much more clearer. Then we have a discussion. Somebody else also raised the hand.
Hello.
Yeah.
So I wanted to ask, like, if there is a particular transaction stored in the blockchain, how do we find that particular transaction?
Yeah. I will give you the examples also here later. So let's cover the very the concept first, and then I will give you the examples.
Okay, sir.
Yeah, Charu.
Okay,
Charu,
sir. Okay.
yes.
Yes.
Yeah, please, Charu, go ahead.
Hello. Sir, am I audible?
Yeah. I can hear you.
Sir, I wanted to ask you that if there is a particular transaction stored in the blockchain, how do we find that? How do we find that particular transaction?
Yeah, I will come back with these with examples in the later slides. So
She
then you will
she
understand.
she might be confused in the sense that whether we are going to store all the transactions in the data field or only Merkle root will suffice. We will be storing transactions somewhere else or storing transaction with the trees in the block. I think she want to ask this.
Is this the question?
Yes, I think that she is asking.
Yeah. So the header file, in the header data, you will have only the Merkle root.
Okay, sir. Okay.
And then, yeah, and then the header file will ultimately look like this. So the first the first one is the version, and then the second numbers you can get the numbers that you can see there, the previous hash, and then next one is the Merkle root of the transactions included in the block, and then the next one is this timestamp, and then beats and then nonce. We'll talk about these things a little bit more on the next slides. Yeah, so let's take a look of this, this rough mining process. Uh, so on a high level, the process of mining boils down to the following steps. So what you do from the network, so what the miners basically do from the network, they retrieve the previous block hash. Uh, because you need to have, you need to point to the previous block. So you need to retrieve, or the miner need to retrieve the previous block hash, and also the target level. And then it has to find, it has to retrieve the transactions, the unconfirmed transactions that took place. So once, so so the transactions included in the candidate block needs to be found out. So let's say 5 or 10 transactions were there. So you need to select them, and then you need to the miner needs to construct a Coinbase transaction. Here it means that, let's think about Bitcoin. So when the miner finds a block, it gets a reward, right? It gets a reward. So that reward transaction needs to be also created. So then this means that you have all the transactions that took place in the network around that time, plus a new transaction that is this new money creation, new Bitcoin creation, new incentive. So that is also that is also there. So all these transactions are there. And then based on that, you calculate the Merkle root of all these transactions, these Coinbase transactions and the selected transactions. And then you concatenate these values to create the block message. And then select a number for the nonce and append it to the block message. So, it's kind of a loop. So you choose a nonce, you choose a number and append it to the block message. And then the full candidate block will be created. And then you perform this SHA-256 hash on the block header and compare the result to the network target. And then if the block header hash satisfies the target, the block is valid, and the miner then propagates to the network that, okay, he has found the block. And then if it doesn't satisfy the target, then the block is invalid. Then it continues the loop. It tries with a new nonce. So I think from this picture, it will be much more clearer. So let's take a look. So as I was saying, that you need the miner chooses all the transactions that took place. So here you can see the choose set of transactions from the mempool. So all the transactions that took place, you take them. Okay, and then build Coinbase transactions means the new money, the or the incentive that once you find a block, so you get a new money, new Bitcoin, you generate new Bitcoin. So that transaction also you build. And then you you query, make a query of the previous hash, as I was telling in the previous slide, and you also query about, or you means here, the minor queries about the target level, and so on. And then, as you can see, that from this transaction, coin-based transaction, and then all the transactions that took place, you calculate the Merkle root. And then with the Merkle root, you can, you concatenate the Merkle root with other things like version, and then what is that? A previous block hash, and so on. You concatenate everything and then create a message called M. So you add everything together, and then you have a message M. And then you choose a number. For instance, let's say choose 1, choose a nonce. Let's choose 1. And then what you do, you concatenate to the block header. So header is like M, the message that you have created, and nonce means 1. And then you calculate the SHA 256 out of this header. Okay? And then then take a look. If this new, this hash value is fulfilling the target. If it fulfills the target, this means that you found the block. If it doesn't fulfill the target, then you go back to this choose nonce and increase your nonce here. Maybe now this time you choose 2, and then do this whole thing. And then if it doesn't work, choose 3 and 4 and 5 and 6 and 7 and so on. So this loop continues until you satisfy the target. And once you satisfy it, then you propagate that you found the block, and then all the peers confirm it or add it. So this is the rough mining process. So as you can see that in this header, only the Merkle root is stored. And you need to also understand that Bitcoin blocks are by default 1 megabyte. So it cannot really accommodate too many things. And they have been structured. The structure has been predefined. So in the block, Bitcoin has been designed in such a way that you store Merkle root in the header. Okay. Then some practical example on how blockchain works, especially, as I was mentioning the previous slide, this SHA 256 function. So this is the hash function. So as you know that hashed outputs are fixed length even though the data varies. So whatever input you give, it always comes back with a fixed length hashed output. For instance, if you put a text, let's say the text is the business strategy in digital economy. If you put this text, the hash output of this would be something like this. But then if you put a comma, just one comma in this red color, one comma, the hash will completely change. And you can put, whatever things, you can put the whole website. Still, the hash output would be the, same length. And what is very important here, that with a little change, with a very little change, the hash output also changes. So for instance, here just adding a comma completely changed the hash output. Now I will show you these things from these websites. Then things will be much more clearer, and then you will understand how this blockchain, the blocks work and this mining process work a little bit more. You will understand. Now, let me show these things. I will now stop sharing and then I will share something else. Give me a moment, please. Okay, do you have any question? Somebody has question? Where is it? Yeah. Okay, can you see this public key, private key thing that I am showing now? Yeah, can anyone confirm? You can see?
Yes, we can see.
Okay. Okay, so I think you probably know about this, public key, private key pairs thing, but just for them who doesn't know. So there is this public and private key pairs. So this is, let's say that if you change a little bit here, you will see change of the public key. So as the name defines, public key is public. You can share it with anyone, but private key is private. You don't share it with anyone. But they are kind of, they point to each other. They have a link between them. So this is this is the private key, public key concept, and then public key could be, for instance, your wallet address, Bitcoin wallet address. That's public key. You can share with anyone, but then that wallet address has a private key. Only with the private key you can see what kind of funds you can make transactions, how much money you want to send. So only then you need the private key. So just for your information, that this kind of public key, private key pairs are there, and they are linked. But then it will understand more when we look at these signatures. So let's say that I want to. This is my private key. As you can see, this is my private key 66 something, and I want to send a message to Divya. Maybe this message I want to send. Hello. And what I will do, so I know my private key, so I will sign it with my private key. And then this is the message signature. This is the message I will send to Divya. And let's say that I sent it to Divya. And then Divya has my public key. So verify, I click verify. So here, maybe this Divya has received my message. For instance, I have written hello, but Divya knows my public key. And he can now verify if I am the person who sent the message. So he has the public key, he has my public key. And then if he clicks verify, then it shows that yes, this is the message I have sent. But let's say that someone in between changed my message to, let's say, like this. and it reads to Divya like this, hello HHH. And now Divya wants to verify, and he will find that, well, something has gone wrong. So this is not the message that I sent. So this is how this public key, private key thing work. So public key is public, and the recipient knows. And private key is the key through which you sign your message, sign your data, sign your transactions, or whatever. And let's now, so this was a simple message sending, but let's think about transactions, sending transactions, making transactions. So let's say that I want to send Divya $20. And form, this is my wallet address. Okay. This is my wallet address, and this is to Divya's wallet address. Okay. And I have my private key. So I sign it. Okay, I sign it, and then I send it to Divya. And then maybe Divya has received the money, and he just want to check whether I really sent him $20 or not. Or anyone who wants to verify whether I have really sent the $20 or not. So he can just verify because he has my public key, and he can verify it. And if there is some problems during some, then he will see that maybe there has been some issues. It's not verified. So this is how you sign transactions with your private key, and then other person can verify, use your public key. And then let's now stop here, and then I will show you another thing about hash. Yeah. So about hash, as I was telling that in Bitcoin, for instance, or in blockchain, we use these hash functions. For instance, this SHA-256 hash is used. So whatever you will write, a new hash is generated. So you can, as I was telling, that all the time, whatever you write, whatever the length of the input data, the hash length is fixed. So this is the hash that is representing this data. Okay. So then let's take a look of the concept of block that we have been talking about. So here you can see there is only one block number 1. And we talked about nonce. You remember we talked about nonce, the proof of work signature, or nonce, which we were changing in the loop in the mining process, starting from 1, and then I was saying that okay, let's try 2, 3, 4, until you satisfy the requirements of the difficulty level. So this is, and then this is the data field. So now when there is no data, in this color, it shows that it is mined, and the hash value is this. There's 4 zeros and then some numbers. Okay. And then let's add some data. Okay, and as you can see that the hash function, the hash is changing because we are changing the data, you know, so definitely it will change. But then take a look at this nonce value. So now it is 72608. Okay, 72608. And then take a look at this hash value. So it is started with FA. So if I click mine, it will mine, and the mining has been done. And then after the mining, you can see that the nonce has changed. And then the hash has also changed. So as you can see, the idea here is that it went through. It, of course, it's just a simulator. Most likely, it didn't really go through, the mining process that I showed you in the slide. But you can think this way that what it was doing. It was changing the nonce. So previously it was 72069 or something like that. It was changing the nonce one at a time, and then it was checking the target level to make sure that it is satisfying the target level. And then once it satisfies, then the block is mined, and then you have this nonce, this updated nonce. So this is how one block works. But then if you add something on top of it, again the block is invalid. And then you need to mine. The miner needs to mine again. Or whoever, if some attacker changes some data here, he or she needs to mine again. And something like that. So this is just one example of block. And as you can see that each time I am mining, the nonce is changing, because it is running that loop. It is running that loop and then finding the right nonce. And for your information, this is just for a simulation purpose and very lightweight version of what is the actual process. Okay, and then so now we have one block. We know one block. But then, as you know, that blockchain is about, there will be multiple blocks. So here you can see that we have, multiple blocks. We have 5 blocks here. Okay, 5 blocks. Block 1, 2, block 5. And they are mined. And as you can see already, that there is a new field called previous block. So here in the previous here we had only hash, but we didn't have the previous block. But now we have this previous hash. And as you can see, let's take a look on this block 5. The previous hash. Look at the previous hash 000 AE. So this is the same number as the hash of block 4 0000 AE. So it is pointing. And then block 4's previous hash 000B is same as the previous as the hash of block 3. So they are pointing each other, just like the figure that I showed 1 hour ago or so. Okay, and as you can see that all are mined. Now let's say that we add something on block 5, and when we add something to block 5, as you can see that this block gets invalid. The hash is invalid. So you need to mine again. So if you mine again, then it will again point to the previous block. Otherwise, and then of course nonce is changed. So what is the point? The point here is that, so when I'm changing something here, only this block is going invalid. not other blocks. All 4 blocks are still intact because we just change this block, and then once we mine, then it again works. But let's say that if we change something from block if we change the data in block 1, for instance, here like this, as you can see that all the blocks are now invalid. And sorry, yeah, so all the blocks are invalid, and the attacker needs to mine everything. So first he has to mine this one, this block 1, then block 2, block 3, block 4, and then block 5. So everything he has to remine to make sure of the changes. So this is why I was saying in the previous, when I was giving you an example, that it is very difficult, I mean, it is much more difficult to change something in the older blocks than newer blocks. So this is one example of simple blockchain, simple blocks. And then, but as you know, that blockchain is basically distributed. So it's not like one computer keeping all the data. So it's actually multiple machines, as we were discussing. So here you can see peer A, one machine, maybe peer B, peer C. So the same thing, idea is same, but the things are in distributed form. And if let's say one peer is under attack, still the data is there in other pairs. Okay. And then yeah. Then how does it really work? For instance, when we transfer money, right? When we transfer money. So previously the examples were about only about the data field. If you look at the data field here, data you can just add anything, right? But here here we are talking about transfer of money. So for instance, in block 1, these are the transactions are happening. So for instance, this Darcy is sending money to Bingley, $25. And Elizabeth is sending money to Jane, $4, $4.27, or something like that. So these are the transactions, okay, in that block. And then a previous hash, because this is the first block, so previous hash is all 0. But if you take a look on this, block number 2, then the previous hash is pointing, block number 1. And this, this money given. So let's say that if we change something here, everything is changing. So then you need to mine again. Okay. So this is the example of transactions in blockchain. And then, yeah, this is not the one I wanted to show, but then there is another one, this one. Yeah. Then where does this private key, public key comes into account? If you want to understand that, then we will see here this. So let's take a look of block 2 here. So block 2 has, nonce, and, then some transactions are there, right? And in the transaction, you can see that that instead of, names sending money to one person to another, the wallet address has been mentioned. This wallet address has sent some money to this wallet address. Okay. And how much the money has been sent? $10. And this is the signature. This is the signature with the private key has been sent. So this is this is what has been sent. Okay, and then the rest of the things are pretty similar. Now let's take a look. Let's take a look of changing something here. So let's say that in the first transaction, I change something. Instead of $10, I make it $5. And the moment that I do, it can be verified. You can see that, the block is not valid, but then the signature also not valid because of this, this private key, public key pair. It is easy to, understand that this signature, something has been changed. Instead of $5, instead of $10, something has been changed. So as you can see here, there are different types of security already with this simple example you can see. So you can see that the transactions are signed with private keys, and then hashes are calculated, and then this mining process takes place. Mining process is there, and then it is stored. Blockchain is stored in multiple computers, multiple nodes. So you can imagine that it is very much secure. Okay. Okay. Any questions so far? Any questions so far?
Yes, I have a basic question.
Yeah, please.
So this during this consensus process, so the data is verified by all the peers, right? And they sign, they do the digital signature. Are they verifying the signature during consensus? How do they make sure that it is these are signed correctly? During consensus, are they verifying the digital signatures as well, or just verifying the data?
They are verifying the data. They are verifying
Verifying
the
that the
data.
signature verification is not happening during the consensus, right?
That's a good question. That's a good question.
Because I
I
have
need to
been
check
recently
that.
working on one work, so I had this question in my mind. I was designing one quantum based algorithm, so I had this in mind because to verify the quantum protocols and all, it will take too much time.
Yeah.
Then how
Yeah.
do we get the throughput, better throughput in such cases? So this is one question I had in my mind.
Yeah.
Okay.
Yeah. I need to double check. But Divya, do you know?
Even I'm not sure. I have been asking many people like us. I'm getting both responses. Some are saying it
Yeah.
is verified, and some are saying it's not verified. So even I am thinking about the
Yeah.
same question.
Yeah. I didn't really look very deeper into the
Mhm.
codes of the consensus algorithm, the proof of work at least. I didn't really dig deeper. I'm pretty sure that you will find the code somewhere, the Bitcoin code somewhere, you need to go into the code. Then maybe it will be much more clearer. So instead of
Okay.
asking, yeah, I think search. I think because the whole everything is open source, so I think you will find it out.
Okay.
Search and then check what is really doing. But this is a very good question. Very good question. I have not also thought about it. Yeah.
Okay. Thank you, sir.
Yeah, but Divya, do you know Divya? If you are here,
I feel that signatures are verified.
signature is verified. Okay. Yeah, it could be. Otherwise it doesn't make sense. It should be. Otherwise it doesn't make sense. Yeah. Yeah, because you do the whole thing, but then you are not verifying the signature. I mean, it doesn't make sense. You are mining it, you are doing so much computation, but you are not doing the basic thing. So how come? So yeah, I think it is more logical that maybe I think the signature is verified. Yeah.
And what I have seen in the implementations that uh, before mining the D apps that are responsible for putting the transactions, they are itself doing this once the signature is verified only.
Okay. 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 Any more
So
question? Yeah. 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 Please go ahead. Divya, go ahead. So
um, once we have committed any transaction,
yeah.
then the process of committing the process that starts with the initiating the transaction and then putting that transaction forward for miners.
Hmm.
So this process, this the verification is an important part of this process.
Yeah.
Pravisha, so
Yes, sir.
as you said that can you
Mm.
elaborate this further that what where you have stuck?
No, see, so I was working on some modification of the practical Python and fault tolerance algorithm. So there, I was thinking of developing my own digital signature scheme, like signature scheme. So there, I thought of implementing post-quantum multivariate signature scheme into that. Then that's where I had, to verify that it requires a lot of computational power, right? So then I was thinking, whether I should go with lightweight digital signature schemes or whether even that post-quantum digital signature scheme will work in my. So my target was to improve the throughput. So for that, I need to, develop something lightweight signature protocol so that even the verification becomes easier. So this is where I was thinking, how can I
we
make
we
it
have worked we
practical?
have worked on this thing in a
Mm.
different aspect that using different algorithms for different applications. That is, for example, you are dealing with some um, let us suppose you are sending some information over an email. So
Mm.
if you are sending a hello message, it requires I think it may be gone without any encryption also. However, if you are sending some information, some particular information or some document, it might require some level of encryption. Or if you are sending some military operations, the information pertaining to military operation, it will require a second level of encryption. So it depends on the type of the information that has been channelized.
Okay.
So you can consider thinking in this way that how to choose a particular algorithm, a particular level of verification for a particular application or a particular piece of information.
Mm. Yes. Thank you for the input.
Okay,
Thank you.
okay, sir.
Yeah.
Please continue.
Yeah. 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 Let me still share the screen and then yeah. How much time do I have today, Divya?
Sir, you can continue for further 15 minutes,
15
15 to
minutes.
20 minutes. You
Okay.
can continue.
Okay. Okay. So let's talk about properties of blockchain. But the first thing that I want to ask you, what do you think from the examples that you have heard so far? Don't you think that blockchain is just a database? Is it just a database and complex database, which has which needs much processing power? What is your opinion? Anyone? Okay, but maybe I can briefly explain. So yeah, so somehow it is actually a database, uh, but uh, but it blockchain is a write-only database, and new entries are appended to the end of the chain on a write-only database, and no one can delete or modify data like the traditional database, where the administrator can delete or modify the data. And of course, we all know now that blockchain is decentralized by design, and whereas centralized relational database could be centralized. Yeah, so this is just the same thing. We know about it. Then let's think about the properties of blockchain. So there are four basic properties of blockchain. The first one is transparency. And in the morning, already somebody mentioned about transparency, immutability. Of course, also you have mentioned about immutability, and then trust and autonomy. So these are the four basic properties of blockchain that I'm going to talk about. And then the first one is transparency. So if you think about this traditional database, it uses this create, read, update, delete model of operation. And then only the most recent version is visible. And most likely, if something is deleted, it's not visible. Values can be created and modified anytime after the creation in normal database. And the central body can do anything to the centralized database. So this whole thing kind of limit transparency. But as you know that blockchain allows only appending, and the history is visible and unchangeable. Anyone can verify the data. And you can read all data of Bitcoin history. You can access what happened to the Bitcoin network. What kind of transactions took place. Everything you can read. In fact, in this website, if you search with the wallet address, or you will find all information. This blockchain.info. So anyone even with this from this website, anyone can verify the transactions, and which wallet contains how much, how much money, and so on. And blockchain, as said, that is a decentralized storage. Yeah, well, I really kind of recommend you to go to this website, this blockchain.info, and then you can check all transactions, both for what is that? Bitcoin and Ethereum. And you will find also there, the headers, and then you know the blocks and their headers. Many information you will find. Those are interesting to view and very easy to view. Just with the web browser you can view. So everything creates transparency. And then the next one is immutability. So as you have seen that each block is linked with the previous one, creating a cohesive whole. Transactions are digitally signed by the creators. So an attacker must gain the private key. The block structure is predefined. Attacker cannot change it. And the chain is created with hash functions. In the example you have seen, many hash functions have been used. Each block is digitally signed by its creator using the consensus algorithm. And then all these things achieve immutability. So once the data is there, no one can change. And then the next one is trust. Why it is trust? Because you trust in something when you know that it is transparent and when you know that it is immutable. And what we are doing here, we are transferring trust for intermediary to technology and multiple actors. So in the past or in the traditional systems, we have to rely on Google, Facebook. But now what we are saying that we are transferring the trust to technology and multiple actors, multiple peers. And then data is stored in through cryptography. And consensus algorithm is used as mentioned. So it creates trust by default. So trust is there by default in blockchain. This autonomy thing is very important because there is no intermediary, as we are saying, that the transactions could be peer-to-peer, no bank involved. So this means that freedom or make your own decision, not dependent on third parties, lack of complexity. In fact, if you have smart contracts, they can be automatically executed. So lack of interventions are needed. So that's why I have written like smart contracts. It improves autonomy and it reduces human intervention. So this is just whatever I have said. They are said in this YouTube video. Similar thing. Types of blockchain. Can anybody tell me what are the types of blockchains?
Permissioned and non-permissioned blockchain.
Yes, very good. Anyone else? Is there any other name? Yeah.
Sir, public blockchain,
Yeah.
private blockchain, hybrid blockchain.
Yeah, exactly. Yes. Good point. Yeah. So normally, as you said, we have mentioned this public-private blockchain is there, and then permissioned and permissionless blockchain. So public blockchains can be permissioned or permissionless. Permissionless means all nodes can do whatever things, can read, submit, validate transactions. But then public blockchains can be permissioned when all nodes, for instance, can read and submit, but only authorized nodes can validate transactions. So some kind of permission mechanism is there. But in permissionless, there is, everyone is allowed to do everything. And private blockchains, only authorized nodes can read, submit, and validate transactions. Yeah. These permission blockchains are mostly used for these enterprise solutions. For business use, mostly permission blockchains are used. And these completely open public blockchains are used only when, let's say, for the case of cryptocurrencies and so on. I think it really depends on the case, on the use case. Uh, yeah, so I think this is kind of the similar concept. The enterprise blockchain could be completely private, completely private or consortium based. Means that okay, few companies together build a blockchain. But if it is a completely private, one organization doing it, there is no point of having a blockchain. If it is completely, only one organization is there, then it doesn't make sense. That's kind of a central, then almost like a centralized system. Yeah. Now I would just use this, next 5-10 minutes before I end for today's lecture. I would just ask you these two questions. Think of a practical problem that you think a private blockchain can solve, and think of a practical problem where a public blockchain can solve a business problem. A business problem or a societal problem, a governmental problem, anything you can think of. Yeah, just yeah. So any thoughts on it?
So enterprise problem could be like supply chain management
Yeah,
because there are multiple stakeholders involved.
yeah,
So there are many interdepartments are
yeah,
also involved. So
yeah,
they basically focus on their own benefit,
yeah,
but not as the system of whole.
yeah,
So in that case, private blockchain could be helpful.
yeah, yeah. This consortium or private blockchain, yes. Yeah, yeah, and for your information, I think one of the most popular use cases of blockchain has been supply chain, and where there are maybe 10, 15 companies, organizations in the supply chain to improve the supply chain visibility. So yeah, so that's a very fair and very popular use case. Anything else? Anyone wants to, any other use case anyone wants to bring?
Maybe healthcare data. So this healthcare data is sensitive. So we may use
Yeah,
private blockchains to store data within
yeah,
some hospitals. And if they have many hospitals all over the world, we can use consortium blockchain to connect
yeah,
them.
yeah, yeah. I think yeah, that's also a valid use case, and not only that, because I think you could use also this consent management, and you can trace who is using your data. So yeah, so that kind of facilities can also be implemented in such system. Yeah, yeah, that's
So,
also a
so
good
I
use
have a
case.
question.
Yeah,
So does ransomware attack can be prevented with the help of private blockchain? Means like in case of healthcare. So
hmm,
last year, there is AIMS in India.
hmm,
So its health database, means patient records were encrypted by some attack, cyber
yeah,
attack,
yeah,
which basically was a ransomware attack only.
yeah,
So I was curious that whether private blockchain could help us to mitigate this problem.
yeah. It could definitely it could, but then again, the problem also is that yeah, as said, that blockchains in general is very secure to different attacks, but then also you need to also think of the investment. I mean, is it is it is it worth to change the existing system to blockchain based system? Because maybe in India, maybe it is possible. I do not know, but let's say if you think about Finland, the systems are already secure, and then the citizens trust the organizations maintaining their data. So here in Finland, I think these blockchain-based systems didn't really get that much popular, and they think that it's just huge investment for some new system. So
Yes,
yeah, so
because
the
in
answer
supply
is
chain,
yes. Yeah, the answer is yes. But then also about this cost effective, whether it is cost effective or not, that's also another point of discussion. Yeah, please go ahead.
sir, because in supply chain management, what happens that large industries are involved.
Yeah,
So they, when they are investing that amount of money, they are getting
yeah,
huge return.
yeah,
But like some small institutions, when they try to deploy this technology,
yeah,
then the investment could not yield that much return, I believe.
yeah,
That's why.
yeah, yeah, yeah. This is one thing, and then the other thing is that other thing is that if you want to do a blockchain, then it also means that all the parties involved need to follow the good practice. So and the question is, do they want to do that? I mean, it's very difficult to somehow bring all stakeholders agree to do certain things. I can give you an example. For instance, we developed this certificate verification platform for that I mentioned at the beginning, that we want to verify when you apply to Finland. For instance, when you apply to Finland, then how do we verify that your certificates for your institutions is authentic, or the work experience is authentic? And if you want to really do that and implement it, okay, so we have developed the proof of concept, which is easy. But if we really want to do it in a way, then all Finnish universities should join the network. Should agree to this process. And then not only that, on top of that, maybe like some companies, some organizations, or let's say the institutions from India, or so you need to bring many stakeholders to the network, to and agree with the practice, and which is very difficult with a small budget and so on. So this turns to be a huge project at the end. We just developed the proof of concept, but we couldn't really, and then tested it within a very small group of network, with a smaller network, but we couldn't really scale it because scaling it requires huge effort.
So I believe Education Ministry of Finland needs to be involved in this
Yes,
as a,
yes,
as a policy making thing.
yes, 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 yes. So most of the things about blockchain ultimately boils down to the involvement of really large entities. Other than, because it's about the network. I mean, it's about the involvement of multiple stakeholders. And if the multiple stakeholders are not involving themselves, then there is no blockchain. Then there is only one single company having a blockchain. That doesn't make any sense. So you need to have different parties. Yeah, yeah. Any more thoughts? Okay. If there is no more thought, then I think I'm done with today's lecture, and then I would like to hand it over to Divya. Dr. Divya, are you there?
So thank you, sir, and I thank you for your first session. It is will be very informative, and
Yep.
I want to convey to the participants